Okay, we're continuing our discussion of the postulates of quantum mechanics. Postulate 1 introduced the wave function and told us that it contains all the information about a system. Postulate 2 told us that we interpret psi squared in terms of a probability density. And so at this point, a really good question is, how do you get other information from the wave function? And the answer is you go to postulate 3. Postulate 3 says, to every observable in classical mechanics, there corresponds an operator in quantum mechanics. Many operators can be built from the position and momentum operators, which are described here. Note in this description, the momentum operator, p hat, this is an h bar, right? And I had previously used, but this is the reduced Planck's constant, 1.055 times 10 to the minus 34 joule seconds. And there's a lot we need to talk about here. So I think we should start with defining some terms. The first is observable. What's an observable? Well, it's a dynamic variable of a single particle that you could imagine measuring in the lab. Right? Something you could go into the lab and measure. So for example, it would include things like position. You could imagine measuring the position of some particle. It would include momentum. Energy. You can measure the energy of a particle. These are all dynamic variables, things which change, which I could imagine measuring for a single particle. It does not include things like mass. Okay, mass doesn't change, at least in this non-relativistic version of quantum mechanics. So that's not dynamic, right? It does not include things like temperature. Temperature is the property of a system of multiple particles. And so we don't talk about that as being an observable, right? The next term that we should define is an operator. And an operator is a general mathematical term for an operation that does something to a function. That's my daughter saying hi. So a couple things. The first is that it's indicated by a hat, right? The position operator is x hat, right? And it is multiplied by x, okay? The momentum operator suggests that I should take a derivative and then multiply that by negative IH bar, right? The second thing is that operators do something to a function, right? So they will always operate on a function. For instance, I can take x hat f. Right? This in language means that the position operator is operating on function f. And what I'm going to do in that scenario is multiply my function f by x. Right? So when the position operator operates on function f, I multiply f by x. If I take the momentum operator and I operate on function f, I get a bunch of constants, negative IH bar, df dx. So in this scenario, I'm going to take a derivative of the function f with respect to x, and then multiply by negative IH bar. Okay. That's the first half of this. The second half of the postulate says that I can build up operators from these two. So how do you build up operators? Well, let me give you a couple examples. Let's say I wanted the square position operator. This would be x squared hat. Right? Say I wanted to measure x squared. Right? This is the operator. X squared hat right? In order to get that, what you would do would be to apply the position operator twice, x hat, x hat. If I do that, I get xx, right, which is simply x squared. If I operate on my function f with the x squared operator, the position squared operator, you simply multiply f by x squared. Let's say I wanted the square momentum operator. P squared hat. Just like before, in order to get P squared hat, you would operate with P twice. This is negative IH bar d dx times negative IH bar d dx. This suggests that I'm going to take a derivative of this function. These are a bunch of constants, so I can move them out front. I get negative IH bar d dx of d dx. This equals negative I is positive I squared, h bar squared. This is ddx of ddx, it's the second derivative. So d squared dx squared. Remember that I squared is negative 1, so at the end of the day, this is negative h bar squared d squared dx squared. And if I operate with my square momentum operator on some function x, what you're going to do is take the second derivative of that function and multiply it by negative h bar squared. That's how I build up operators. There's some operators you need to know. The position operator, the momentum operator, and then 3 others, the kinetic, the potential, and the total energy operators. Let's talk about these. Kinetic energy. You probably remember an equation which looks like this. Ke equals 1/2 mv squared. Physicists write this in a different form, or sometimes write it in a different form, which relates it to the momentum. Remember that momentum is mass times velocity. So I can write this in an equivalent way as p squared over 2m. So in terms of momentum, kinetic energy is momentum squared divided by 2m. You might see where this is going. We often call the momentum operator T hat. The idea is that you're associating it with kinetic energy, right? With temperature, sorry. T hat would be 1/2m times p squared hat. We just derived this. 1/2m negative h bar squared d dx squared. Putting it all together, the kinetic energy operator is negative h bar squared over 2m d squared dx squared. You should know this one. Write this down. Potential. This is given the symbol V hat. And what I would tell you in general is that this depends on the specific situation involved. So different systems have different types of potential energy, right? one example might be a spring. You may remember that the potential energy for a spring is 1/2 kx squared. And so in this scenario, the potential energy operator V hat is equal to 1/2 kx squared, which is 1/2 kx squared. You might imagine another situation with potential energy, right? It could be a Coulomb attraction. In this case, it's Q1, Q2 over 4 pi epsilon 0 R. R is the separation between things. In this scenario, V equals Q1, Q2, 4 pi epsilon 0, 1 over R hat. What is this operator? Well, as you might guess, it's simply 1 over R. So that's the kinetic energy, sorry, Coulomb attraction, right? Electrostatic potential. And so in the case of potential energy, the specific form of the kinetic, in the case of potential energy, the specific form of the operator depends on the situation. So remember these guys. This one depends, but you should be able to derive it. Last one I told you was the total energy operator. This is perhaps the most important operator. It's given its own name, which is called the Hamiltonian, right? H hat. Hamiltonian is not this guy, right? It's named after this guy, William Hamilton. I don't know if you can read this, it's blocked off, but he basically developed a formalism to apply Newton's equations of a motion to any coordinate system. And in order for it to work, you need to know the total energy of the system. That's why it's given this name. H hat is equal to kinetic plus potential. Right? Kinetic always has a common form. Which looks like this. It's the second derivative. It tells me something about the kinetic energy of the system. And the potential, we leave in its most generic form, which is V hat, right? Again, this would depend on the specific situation. So this is the kinetic energy. This is the potential, and it depends. Okay, those are our operators. In the next video, I'll tell you about how we use them, and I will see you then.